So now the last thing I want to talk about, unless I decided to add something later, is functions acting on sets. So we're going to start off just looking at the definition of image again. Now, before we looked at the image of a function, so that's typically when you look at the image of the entire domain, but we don't have to do that. We can just look at the image of a subset of the domain. So let f go from S to T. If A is an S, contained in S, then the image of A under F, okay, so this is the full name for it, image of A under F, is the set F of A, where F of A is equal to F of X, such that X is in A. Okay. So, and if there's no confusion about what function is being used, then you might just say the image of A and leave out the under F part, right? So the image of a function typically would be F of S then, right? F of the entire domain, also sometimes called the range, but again, that word has a little bit of ambiguity depending on what text you're reading. Like this text I'm reading that I'm referencing for this, for example, does call that the range, but there are other books that refer to the range as the codomain. So I just try to stay away from that word in this context. But in this case, this is just the image of some set, which is a subset of the domains, not necessarily the image of the entire function, which would be represented by f of s. And then, of course, we can talk about the preimage, which we did talk about, but not in terms of a set. We only looked at for a specific element. So let f of s to t, let me call this definition. If C is contained in T, so this is in the codomain this time, then the preimage of C under F, and again, you could just call it the preimage of C if there's no confusion about which function you're talking about, where F inverse of C is equal to X in S, such that F of X is in C. Okay. So, important to look at what the different points are. So the F of X points in the image, right? Those are elements. I didn't actually write it out. The definition doesn't actually write it out, but those are elements of T, right? Maybe I'll just go ahead and expand that just for consistency between these two definitions, right? Such that X is in A. So it doesn't necessarily cover all of T, but these are elements of the codomain T. So it's a set of the outputs essentially. And then the F inverse is a set of the inputs, members of the domain. Okay. So when a function acts on a set, it's basically like you're taking every single point in that set, sending it through the function, and then whatever the outputs are, that is the new set. The set of those outputs is your new set. So f of a would be a set, right? Now, again, f inverse here does not need to be a function. It's not defined anywhere that it is a function. F is defined as a function. F inverse is not defined as a function. So you can still create this set of F inverse without F inverse being a function. It just is some other thing. It's a set, right? Or a relation if you prefer. Instead of preimage, sometimes we do use the word inverse image. I would say I've probably heard that more than preimage, but I couldn't say for sure. But it is very common to call it that instead. So this leads to some interesting theorems we can do when we start talking about, well, what happens if you put the union of a set through the function, or what happens if you put the intersection of a set through the function. Okay. So this theorem here says, let f go from s to t, and let a be contained in S, B be contained in S. Okay, yeah, so they're both contained in S. Then, first we have f of A inverse B is a subset of f inverse A intersect f inverse B. Or, so I don't know why I said inverse. F of A intersect B is a subset of f of A intersect f of B. Okay. And then 2, f of A union B is not a subset, actually. It's equal to f of A union f of B. Okay. So this is a little interesting that for the union, they're actually the same set. But for the intersection case, it's only a subset. So if you wanted to prove the second part, you would need to show both directions, right? So let's go ahead and go through the proof of part 1. Okay. So proof of 1, let's say. It's a little bit shorter than the proof of 2, since 2 you got to take both directions. So take y in f of A intersect B, which of course is, this is going to be a subset of t, right? Since that's the codomain of t, right? So if y is in f of A intersect B, it is in t, which might be helpful, maybe not, but just something important to note here. So we just need to show now that this is in f of A intersect f of B, using the definitions of the sets that we've come up with. So because x is in, or because y is in f of A intersect B, then there exists an x in A intersect B such that f of x equals y, right? This is just the definition of a function. And then since x is in A intersect B, we must have x is in A and x is in B, right? This is the definition of the intersection. So we're just kind of following the definitions here, invoking whichever ones are useful at this particular time. Now, x being an A and f of x equaling y implies that y is an f of A, right? Again, just following the definition of a function, right? The outputs lie in the image of A. And then we can do the same thing with x being in B, right? X being in B and f of x equaling y will imply that y is in f of B. So thus, y is in f of A intersect f of B, right? Because it's in both of them. Okay. So not too bad of a proof, just again, just invoking all of these different definitions we've had of functions, of sets of the image, and so on and so forth. All right, so now let's look at the similar theorem for inverse functions. Let f from s to t be a function, and let c and d be subsets of t. Then, number one, f inverse of c intersect d is equal to f inverse of c intersect f inverse of d. Okay, so note the equality this time. Also note again, f inverse doesn't have to be a function, so maybe that's a reason we get a equality this time, right? A little bit of a less restrictive definition. F inverse of C union D then also has an equality. So they both have equalities this time. So with functions, one of them does not have an equality, only a subset. For the inverses, I probably said inverse function because that's just naturally what I say, but again, it doesn't have to be a function. The inverse, F inverse, that set, we get equality for both of these. So the proof will follow, like all of the different proofs, like the proof for, part 2 on this one, and the proof for 1 and 2 on this one will all kind of follow the same way. This one is a little bit trickier because you're working with inverses, right? So you have to kind of like flip back and forth a lot. So it's just a little trickier, but if you're careful, it pretty much follows the same path. But again, they basically just boil it down to take some element in this set, show that it's in this set, and use that definition of the inverse along the way. You can't use the fact that f inverse is a function because it's not a function necessarily, right? So you don't want to use anything regarding that, but you can use the fact that f itself is a function. So again, it's a bit long. I'll go ahead and do the proof of one of the directions for one of these. So let's go through the proof that f inverse of c union d is a subset of f inverse of c union f inverse of d. So that's the opposite of the one we did last time. And then if you want, you can go ahead and go through the other direction, which might be helpful practice of proofs once again. So we're going to go ahead and take some element of x in f inverse of c union d. Okay. Then that means that f of x is in c union d, right? So this follows directly from the definition of the set, the inverse set. If you go back and look at that, right, that this is just what this means, right? That f of x is in this part right here. So this means that f of x is in C, or f of x is in D. So we have two cases we have to consider here. So we'll say if, sometimes people write this as like case 1 or case 2. We can just write it as like a sentence though. If f of x is in C, then x is in f inverse of C, right? Again, just the definition of what an inverse set is. Like you can kind of think of it like take the f inverse of both sides of this, even though that's not really like proper, but that's a good way to remember it, right? This isn't like an operation you can take. You can't really do math on both sides of this or anything like that. But that's kind of how I like to remember it. Is like just bring the f over here. X is in f inverse now, right? And of course, f inverse of C is going to be in f inverse C union f inverse D. That's just the definition of the union. And then if f of x is in D, do the same exact thing. Right, then x is in f inverse of D, which is a subset of f inverse of C union f inverse of D. Okay, so thus f inverse of C union D is contained in f inverse of C union f inverse of D. Okay, so we've shown one direction, the other direction follows pretty much the same way. All right, so a couple other theorems that I want to look at here, because they do kind of highlight one key difference of sets versus like numbers going into a function. Okay, so let f from S to T be a function, and let A be a subset of S, and let T or C be a subset of T. Then, number one, A is a subset of f inverse of f of A. Okay, so they don't completely undo each other like you would get with a number, right? F inverse of f of A is not necessarily equal to A, but A is a subset of it. And then same with the other direction, except the actual direction gets reversed here. F of f inverse of C is a subset of C. Okay, so again, not necessarily an equality here like you would get with a number. So part of this is that f inverse is not necessarily a function, right? We're thinking of these all as sets. So, even though we're writing functions, functions have that particular property of being mapped to one specific element. F inverse does not have that. So you basically need a bijection in order to guarantee that the equality holds, which a bijection means that f inverse is a function. So you just need f inverse to be a function, and then you get the equality. So that makes sense with what we discussed back in Math Tools 1, because there we were only looking at inverse functions. Here, again, f inverse is not necessarily a function, so we don't necessarily get equality. So we'll go ahead and go through the proof of part 1 here. Okay. So we're going to take an A in A, which is a subset of S, which probably won't matter, but just something to note. This is everything we have to work with here. Then f of A is in f of capital A. Again, just by the definition of f of capital A. Then, since f of A is a subset of T, this implies that f inverse of f of A is a subset of S. Right? Again, just by the definition of inverse. We go back to the other set. So these outputs we put back through f inverse, we're back in S, which was the domain. So if we look at this definition, so note that, so it's helpful just to write out what this is as a set. F inverse of f of A is going to be those values of S such that f of x is in f of a. Okay. So why does this help us? Well, note this part right here, right? F of a, little a, is in f of big A. This set is all of those values which are in f of big A, right? Assuming that they originally came from S, which they did, because A was in A, which is an S. So A is in this set, f inverse of f of A. Okay, thus we have the original statement here, which is that A is in f inverse of f of A. Okay, if you wanted to show that it's not equal, you would need to show a counterexample for the other direction. So there you'd want to use some function which does not have an inverse. So like something that's not a bijection, for example.